today, let's talk about the story of a tiny little invention that had a gigantic impact. We're talking about a sliver of silicon that didn't just change the world, it literally built the one we all live in today. I mean, just think about your smartphone for a second. It's a library, it's a movie theater, it's a map to pretty much anywhere, and it connects you to billions of people. How is all of that power even possible in something so small? Well, the answer lies in one single revolutionary piece of tech. So to really get this story, we gotta start with the basics. What exactly is a microchip? Okay, at its heart, an integrated circuit, or IC, as you'll hear it called, is basically a whole electronic circuit. We're talking transistors, resistors, the whole shebang, all miniaturized and printed onto a tiny little slice of silicon. Think about it like this. Imagine taking the entire electrical grid of a city and somehow printing it onto a postage stamp. That's the kind of leap we're talking about. And the difference it made was just staggering. Before the IC, building circuits was this manual, piece-by-piece job. It was a mess. The result was electronics that were huge, super expensive, and honestly not very reliable. But the integrated circuit? It made everything exponentially smaller, cheaper, faster, and way more energy efficient. So who was the genius who came up with this world-changing idea? Well, like a lot of great inventions, it wasn't just one person. It was more like a race between two brilliant engineers who were tackling the exact same problem at pretty much the exact same time. You see, the big problem facing engineers back in the 1950s was something they called the tyranny of numbers. If you wanted to build a more powerful computer, you just needed more parts. But more parts meant more wires that had to be soldered by hand, which meant more places for things to break, and these giant power-guzzling machines. The entire field of electronics was just hitting a wall. And then, bam, a breakthrough. In late 1958, an engineer at Texas Instruments named Jack Kilby showed off the very first working integrated circuit. But just a few months later, another guy, Robert Noyce, over at Fairchild Semiconductor, came up with his own version, and it was way more practical. The digital race was officially on.
Now, even though both of these were groundbreaking, their designs were totally different. Kilby's was amazing, but it was really a proof of concept, a brilliant but kind of clunky assembly of parts. Noyce's design, on the other hand, was what we call monolithic. Think of it like it was carved from a single piece of silicon with all the connections built right in. That was the design that was made for mass production. That was the blueprint for the future.
So Noyce's silicon chip was the key, right? Well, almost. One more piece of the puzzle was needed to really unlock its potential and get us to the kind of insane density we see in chips today. And that brings us to the true hero of our story, a tiny but mighty component called the MOSFET. This specific kind of transistor would become the fundamental building block for, well, everything in the digital age. So what was the big deal with the MOSFET? What made it such a game changer? Simple. You could make them incredibly, ridiculously small. You could pack them super close together on a chip without them interfering with each other. And that meant more power in less space for less money. It was the perfect recipe for a revolution. And this is where things get really wild. This incredible pace of growth was famously observed by Gordon Moore. He predicted that the number of transistors you could fit on a chip would double roughly every 2 years. Now, this Moore's law, as it came to be known, wasn't really a law of physics. It was more like a target, a shared goal for the entire industry that drove this relentless competition and basically guaranteed our devices would get insanely powerful and cheaper year after year. So just how fast do things really move? Let's take a look at the actual generations of integration to really appreciate the kind of exponential growth that Moore's law was talking about. Look at this. In just 20 years, we went from, maybe 10 transistors on a chip to over 1 million. Each new generation, from small scale to ultra large scale, was a quantum leap in computing power. It's just mind-boggling. And today? Well, today, a high-end processor can pack in over 53 billion transistors. Let that sink in for a second. 53 billion. It's a number that's almost impossible to even wrap your head around. Here's another way to think about it. The same amount of computing power that once filled an entire room now fits comfortably on the tip of your finger. That is the power of integration. All right, so we've got this unbelievable technology, but it didn't just stay locked up in a lab. From the very beginning, it was put to work solving some of humanity's biggest, most ambitious challenges. And you might be surprised who the first big customers were. Aerospace and defense. It was the US government's huge demand for lightweight, super reliable computers, for things like the guidance systems and Minuteman missiles, and of course, NASA's Apollo program that put a man on the moon that really forced the technology into mass production and started to bring the costs way, way down. And once those costs started to drop, integrated circuits just exploded into every single corner of our lives. I mean it. They're not just in our computers and phones, they're in your car, your washing machine, your TV, in life-saving medical devices. Look around you. Almost every single piece of electronic gear you own is powered by these tiny little silicon chips. The integrated circuit was the engine of the entire digital age. It shaped the world as we know it. But now, after decades of this incredible growth, we're starting to bump up against the physical limits of silicon. So the question isn't what we can still do with it, but what comes next. Our world is built on silicon. What's the next one going to be built on?